All right, everyone. We're going to go ahead and get started. So hopefully everybody was able to take a quick break, run to the restroom, grab a coffee or whatnot. There's going to be a poll that's going to pop up in your menu that you might see. So please do take the time to answer that when it does show up. We have a number of questions for you throughout this afternoon. Now we're gonna jump to Jaco Baas, who's gonna be discussing kind of integrating transitional flow structures into hybrid event beds and some of the implications for understanding hybrid flow evolution and on submarine loan fringes. And I think this is a really, this talk fits very nicely with what we've actually been seeing presented by everyone, and specifically some of the questions that Nora some of the observations that Nora was bringing up, and some of the questions that we're going to Nora, understanding the lateral continuity and the continuity of the actual stratigraphy, the continuity of the processes. And I think also questions very nicely raised by Zane when starting to understand the complexity of transitional flows that can occur in carbonates as well. So please go ahead. So quickly before you go ahead, Jaco, everybody can answer the quick poll question, and then we are going to start with you in a few seconds.
Can everybody see my screen now?
Yes.
We can, yes.
Okay, good. So this work on integrating transitional flow signatures into hybrid event beds was done in collaboration with Piotr Lapsik from Krakow University in Poland. And Piotr did most of the field work, using me more or less as his field assistant, a very interested field assistant, and he also led the statistical data analysis. I will start with a short description of hybrid event beds, the classical model for hybrid event beds, and also cohesive clay-laden sediment gravity flows that are transitional between turbulent and laminar. Based on new field data from the Aberrated Grids group in Wales, I will then update the existing hybrid event bed facies model by integrating transitional flow signatures, and finally discuss how this model can be used to interpret sedimentary processes, focusing in particular on flow transformations. On the left-hand side here, this is the original hybrid event bed facies model proposed in 2009 by Holton and co-workers that probably most of you will be familiar with. So there's a H1 division at the base, which consists of massive sand formed from a forerunner high-density turbidity current. H2 has alternating bands of sand and mud associated with intermittent near-bed turbulence suppression due to the presence of cohesive clay. H3 consists of chaotically mixed sand and mud formed by cohesive debris flow updip of the high-density turbidity current, and H4 and H5 are essentially a Bauma sequence generated by a low-density turbidity current in the turbulent wake of the hybrid event. Now, in 2011, it was proposed that transitional flow behavior can be used to explain some of the properties of hybrid event beds. As in the original model, H1 and H4 and 5 were associated with turbulent flows, with turbidity currents, although the sandy H1 division can also be formed by a transitional flow supersaturated with sand. Now, it was proposed that H2 can result from three types of transitional flow. Turbulence enhanced transitional flow, in which a relatively low amount of mud causes a strong turbulence in the entire flow. Lower transitional plug flow with more clay that causes a rigid plug to develop above a near-bed layer with enhanced turbulence, and upper transitional plug flow at the highest clay content, causing the plug to thicken and the near-bed turbulence to be attenuated. And was also proposed that H3 represents a laminar plug flow, agreeing with the original debris flow interpretation. However, all those reinterpretations were based only on laboratory data on the dynamics of transitional flows, and they were not validated in outcrop at that time. So therefore, Piotr and I decided to go to the Arithmetic Grids group and the Borth Mudstone Formation in exposed in coastal outcrops in West Wales to find transitional flow signatures in hybrid event beds. And this system is quite suitable for this because the waves in this area have nicely polished the rocks, so different sedimentary facies, including transitional flow facies in hybrid event beds, can be studied in very much detail. And these hybrid event beds were deposited in an elongated deep water basin parallel to the present day coastline, and our focus was on the distal part of the basin, in particular distal lobes and lobe fringes, where mixed mudstones and sandstones are particularly common. Unfortunately, I do not have time to describe the system in detail, so the best I can do is whet your appetite, really. The outcrops are 2D, and that limits them to studies of sedimentary processes. So there's beautiful hybrid event beds with very nice, very well exposed sedimentary structures, including current eliminations, including soil marks, including weird and wonderful soft sediment deformation as well. So process-based work is really what you can do in these type of outcrops. But we did do some architectural work as well, particularly focusing on channel fills in proximal and more medial parts of the system. Now, I work in the distal part of the basin, built on work published in 2020 by Mac and Baker. She described different types of bed forms and linked these bed forms to specific flow types. So she found the classic sandy current ripples, which she attributed to turbulent flows, essentially turbidity currents. But she also found larger ripples, which are larger in height and larger in length than the sandy ripples, and they are associated with turbulence enhanced transitional flow and lower transitional plug flow. And then she also found low amplitude bed waves, which she linked to upper transitional plug flow. So flows with different clay content, really. We used the same lithofacies scheme as Megan did, but we focused more on the vertical stacking of facies in hybrid event beds than Megan did. The large ripples and the low amplitude bed waves are part of her structured muddy sandstone facies. And these transitional flow facies also included heterolithic and banded sandstone and mudstone. Turbulent flow facies included massive sandstone and structured sandstone, mainly containing plane parallel lamination and ripple cross lamination. And then there are various types of siltstones and mudstones formed by either muddy debris flows or through hemipelagic settling. Now, these pictures show examples of how these different facies are distributed, how they are stacked in the hybrid event beds we investigated. And in fact, we investigated a total number of 200 of them and carefully measured the stacking of these different facies. And these are just, 7 examples of our measurements. And here are some more. Again, I don't have time to go in detail, but I'd be happy to show those examples again during the question and answer session. To make sense of this large data set, we did Markov chain analysis to find the most common facies transitions at multiple levels of hierarchy. And this led us to a series of facies transition flowcharts like the one here, and that eventually led us to a facies model for the hybrid event beds in the study area. And shown on this slide is the full facies model, which includes H1, which includes not only massive sand, but also plane parallel laminated and ripple cross laminated sand formed by high density and low density turbidity currents at the front of the flow. In H2, the flow changes from turbulent to transitional due to a higher cohesive clay content, and that's evidenced by the presence of banded and heterolytic facies and also large ripples and low amplitude bed waves. And this shows the greater influence of cohesive forces. And that process culminated in the chaotically mixed sandstone and mudstones formed by debris flows in the H3 division. Particularly interesting is that a repeat of H1 to H3, but in finer grained sediment, occurs in H4 to H5. So we find turbulent flow facies in the lower part of H4, we find transitional flow facies in the upper part of H4, and H5 can be massive and has a hemipelagic origin, or it can consist of mud with silty, swirly structures, which we interpret as muddy debris flows. Now, H4 to H5 does represent deposition from the wake or the tail of the hybrid flow, and the vertical sequence of facies suggests a gradual shift from turbulent flow to turbulence attenuated, and finally to laminar clay-rich flow, possibly as a result of flow deceleration rather than a change in clay content. And that agrees with what Megan Baker concluded in her 2020 paper. The new facies model shows a more gradual change from turbulent to laminar flow, and there's a more gradual flow transformation than in the original model. In an up-dip direction, turbulent flow formed by turbulent flow in high and low density turbidity currents is replaced by different types of transitional flow and then by debris flow. The same flow types may then also develop in an up-dip direction in the wake of the debris flow and possibly ending with gradual settling of mud from suspension. As with many facies models, the full model is rather idealized, and in many beds, certain facies and certain divisions are missing. That allowed us to come up with 3 different incomplete facies models, if you want. A model that is turbulent flow prone, and that is closest to the original Horton et al. 2009 model, except for the fact that our beds not only contained massive sand in the H1 division, but also plain paralaminated and rippled sand. We also found 2 types of transitional flow prone hybrid event bed models, one with a H3 division and another one without a H3 division. And these hybrid event beds tend to be poor in plain paralamination, in ripple cross lamination, but rich in large ripples and low amplitude bed wave facies. So the transitional flows that form beds without H3, we interpret them to may have had enough, not enough clay to, or perhaps were too fast to reach laminar flow conditions. And in general, they also did not enter the turbulent regime often because of the absence of plain paralamination and sandy ripples. So in conclusion, we did work in the arboreted grids group and the Board mudstone formation to study hybrid event beds with transient turbulent flow behavior, and we found lots of examples of those that allowed us to extend the facies model for hybrid event beds by including transitional flow signatures. That in turn allowed us to conclude that the transitions in the transformations in flow may be more gradual than perhaps previously recognized. The original facies model is what we call a turbulent flow, turbulent prone hybrid event bed, which is just one part of a larger suite of hybrid event bed types. Now, H3 divisions, which are characteristic for hybrid event beds, may actually be missing from beds that are more transitional flow prone, and that suggests that laminar debris flows and mud flows may not always develop, especially in the cases that we investigated. Now, let me end with a shameless plug. If you are interested in these sorts of deposits, if you're interested in transitional flow signatures, we are organizing an IAS International Summer School in the July of 2025, where we will showcase the geology of the north and northwestern part of Wales, the island of Anglesey, but we will also visit the Aberystwyth grids and the Borth Mudstone Formation. So if you are an early career researcher and you want to see some beautiful geology in a period of 7 or 8 days, come to Wales and join the summer school. Thank you very much.
Thank you, Jaco. So we'll be taking questions towards the end of this session, but right now we're going to launch a poll question because they went up very quickly and not all of you had a chance. So we're going to launch one poll question right now. And whilst we're making that transition, that's the first time I've seen this flyer from Jaco. I can tell you those outcrops are spectacular. I highly recommend this opportunity. In fact, Jaco, I invite you to put some information in the chat for everybody. So whilst you're taking the poll, just to line up, we've got a few recordings this afternoon. The next one coming up is going to be from Anne Bernhardt, who's a professor at the Freie University in Berlin. We're moving at this point in the session away from the heterogeneity and processes part of the title, more into the new approaches. And this next talk will be relating to new techniques in geostatistical modeling in deepwater geomorphic and sedimentological features in submarine canyons.
Let's go ahead and do one more while we have everyone voting. If the SEPM DRG held a field-based meeting, what would be your response there?
There's going to be a subsequent question to this about location. So
okay.
This is really about your enthusiasm for wanting to have one of these meetings or an associated meeting to this actually in the field.
Okay. So we'll go ahead and get that one closed. We're about up to 60% again. And this one will be the most exciting question.
There's quite a few options there, so take a moment to think about it.
Worked on very hard by the committee today and yesterday. And you can send those other comments back to the committee of location suggestions.
Oh, interesting results.
Yep.
We will share these results when we have them completed.
Yes, and we can share this one, I believe, if everyone wants to know this one. Okay, we're about 60%. So I can close that one and then I can share the results of this one.
So yes, particularly those of you selected other, do let us know where you would like to go. I know this is going to be very driven by people's locations. So.
Okay.
Okay, without further ado, I think we better get to the next one. We're about 15 minutes behind, but I think everybody knows that.
Hi everybody, and first of all, thank you to the organizing committee for putting on this virtual forum and also for inviting me. I'm really sorry I can't be here live today, but Lillian asked me to fully record a presentation. And when I heard about the topics, new approaches to deep water systems, I was thinking about some recent work that I did together with my colleague Wolfgang Schwanger. And I think one of the challenges in deep water sedimentology is that we are dealing with increasingly large geomorphic data sets of the seafloor, and we need to adapt some of the very sophisticated, interesting geospatial modeling tools that are more widely used in terrestrial geomorphology. And so I will talk about this topic and show you an example where we try to explain the global submarine canyon occurrence using a technique called point plans. Now, I was reading this classic paper again a few years ago by Twitchell and Roberts, and they looked at the east coast of the United States and several canyons in here, and they state that canyons are numerous and that spacing correlates with the overall slope gradient. And you can sort of see this relationship in their figure here, where we have the 200 meter and 2000 meter contour line, and when these converge, then slope becomes steeper and there's more canyons. But when looking at this, I was like, yeah, looks like it's true, but it's a qualitative sort of eyeballing technique here, and then isn't really true, right? Here, for example, the slope is less steep, but there's still many canyons. So as we now have really large data sets, for example, this one mapped by Peter Harris and colleagues, published as a paper called Geomorphology of the Oceans, where they mapped canyons that are blind or that are confined to continental slope and shelf and sizing canyons, but also the extent of the shelf and the continental slope on a global scale. So I was thinking, what techniques do we have to apply to do exactly this, but on a large scale and doing this quantitatively? How does the relationship between continental slope gradient and canyon abundance actually quantitatively look like? And then we broadened the research question to, can we predict the global distribution of slope confined and shelf and sized canyons by using, for example, the gradient of the continental slope? Now, we don't have to limit ourselves to the gradient of the continental slope, but there are many global data sets available that quantify parameters that might influence canyon formation. For example, longshore transport, offshore groundwater discharge, the sediment thickness of the continental margin in the marine realm, but also in the terrestrial realm, we quantify peak ground acceleration, the steepness of rivers, extreme rainfall events, the erodibility of the onshore bedrock, for example, as parameters that might influence how many canyons are actually formed offshore. We use point pattern analysis to approach this question, and that's a technique that can identify the underlying mechanism that determine a distribution of points in space. So here is a point pattern. The black dots are points, and the colors in the background are a smooth point density. And this could be the spatial distribution of trees, mineral resources, submarine canyons, landforms, you name it. And then we identify so-called predictor variables, for example, the topographic gradient, the continental slope gradient, and which is defined in the same spatial window as the point pattern, and we can test whether the topographic gradient relates to the point pattern, and if so, how. These are the first order effects where predictor variables control point patterns, but we can also very elegantly test for second order effects if points interact on one another. This is a completely random point pattern where points do not act on one another, but this, for example, is an inhibited point pattern. Think about big trees, for example. So big trees have large crowns, and then the next big tree is not going to grow right next to tree number one because it's going to be in the shade. So by this natural process, these points on the trees inhibit one another somehow. And then the third version would be a clustered point pattern. So we can test whether these relationships exist as well. Now, to make it a bit more complicated, we use point patterns along linear networks because in some cases, the points cannot be randomly distributed in a spatial window, but they can only occur along defined lines. Think about traffic accidents, for example, here in the city of Perth, you see in gray the road network, and then the black dots are accidents that occurred, and of course, these cannot happen just somewhere in space, but they happen along the roads. And as more geomorphic examples, this is an example from Wolfgang, where he models midpoints along a river, could also be a submarine canyon, that of course can only occur along the tail rig of the geomorphic feature here. So that alters the math a little bit, and we use this particular version where we use the center points of mapped submarine canyons along a continental margin, and then we collapse these on the continental slope center line. And we do that because canyons cannot just occur randomly along the continental slope, but there can only be one canyon along each stretch of the continental slope. And so we simplify each submarine canyon to a single point, and this is how this looks. These are the slope-confined canyons along the continental margin of Africa. And then we calculate a smooth canyon density. The units would be canyons per kilometer out of this point pattern. And as you can see here in the colors scale, large canyon density would be 0.08 canyons per kilometer. That's a bit hard to imagine, but that translates to 80 canyons per 1,000 kilometers of continental slope stretch. We use all these predictor variables that I had already introduced, and we add one more for data quality, because where the mathematical data quality is higher, you might be observing more canyons, so we correct for this as well. We then project these predictor variables onto the continental slope, so we have the data in the same spatial window. This, for example, is the erodibility index of onshore bedrock from highly erodible to durable, and that's projected onto the continental slope, so we can then use it to predict slope-confined canyon density. To predict canyon density at each spatial location with the coordinates x and y, we use a log linear function where we calculate the regression coefficient better for each of the predictor variables at each location x, y. So truly spatial approach, and we use the R package SPANSTAT by Bedle and colleagues. This is the model outcome. These are the actual slope-confined canyon densities along the margins of the major continents worldwide, and these are the predictions that come out of our model. So we are actually predicting the canyon densities, the high canyon densities along Australia pretty well, also the eastern tip of the Arabian Peninsula, the Mediterranean Sea, and so on. So we're actually quite happy with the model outcome here. But what's interesting now is what are actually the important parameters that play the most important role in predicting canyons. This is a measure of model performance, and all you need to know due to time constraints is that the DWRG shows or indicates better model performance the lower the values. So if we run the model with only adding the continental slope gradient, the WRG drops significantly, so this is a very important variable. Ship track density as a measure for mathematical data quality is also important, as we expected. And all of the other 15 parameters that we have calculated on a global scale, they don't really do very much, right? They don't really enhance the model performance significantly. So continental slope gradient is the most important predictor variable for slope-confined canyons, and the picture looks similar for shelf-incised canyon slope, continental slope gradient being the most important here, followed by the shelf gradient. And then adding longshore sediment transport and so on really doesn't enhance the model performance much further. And what we can do now is look at the actual relationship of canyon density, indicated by lambda here, in dependence of the continental slope gradient. And we can see the higher the continental slope gradient, the higher the canyon density. So this is where I wanted to get at in the first place, right? This is the actual quantitative relationship of canyon density along the world's continental margins in dependence of the continental slope gradient. For shelf and seismic canyons, the picture looks very similar for continental slope gradients. Also, their density increases significantly with increasing slope gradient, but also with increasing shelf gradient. So to conclude, the global patterns of submarine canyon density can be predicted reasonably well by using only continental slope gradient and the shelf gradient, plus the data quality measure that I have mentioned. And high global submarine canyon densities are favored by high continental slope gradient, and in addition, high continental shelf gradients also play an important role for shelf and seismic canyons. Interestingly, terrestrial processes play a secondary or actually no role in this very large-scale approach that we are using here. So I would say that point pattern analysis actually holds great potential in terrestrial, but definitely also in marine geomorphology and sedimentology. And we can use this to understand the distribution and the formation of deepwater landforms, platforms, and also ecosystems. Examples would be prop marks for, or midpoints along canyon systems. Landslides can be reduced to single points of the data set as large. Coral mounds, sinkholes, sediment waves, mineral deposits, bank failures. All of these features might be interesting to be analyzed with this particular approach. And if you want to read more about this, this would be your Bible, this spectral point patterns by Bedle and colleagues that explains the R package that comes with it. Wolfgang has written parts of it into MATLAB, if this is your favorite world, and has also published a paper on this. We are about to submit the paper regarding the study that I just showed to you. If you have any questions, please contact me, critique, cooperation. If you have a really awesome data set that you think would be suitable for point pattern analysis with the right scientific questions to it, then please do so. And since this is not a talk, these are the references that I showed, and I thank you very much for your attention.
Okay, our thanks to Anne there. As Anne herself has suggested, if you have any questions about the presentation that you've just seen, you can contact her on the email that she displayed. We'll copy that email into the chat again in a minute in case you missed it. Very interesting talk. It reminds me of some of the source to sink studies that have come out globally and along the African margin. There was a good paper in 23 by Ruby et al. In the AGU on a similar topic. I'm sure somehow these are all related to global scale tectonics as well. Moving into the next talk then, it's going to be another recording, this time from Ibrahim Tahiru, who's a student at the University of Liverpool, and he's going to be talking about some numerical modeling that he did for us in some deep water fans. Keep the questions coming in the chat.
Hi, my name is Ibrahim Tahiru. I'm a doctoral researcher at the University of Liverpool. Today I'm going to give a short description, or a short presentation rather, on my work that is entitled Deepwater Fan Hierarchy, Assumptions, Evidence, and Numerical Model Analysis. For many years now, researchers, both in the academia and in the industry, have had interest in studying submarine fan deposit because they tell us a lot about past climatic and oceanographic conditions, and they are also a prime target for oil and gas exploration. So in this work, I'm going to ask the question: do hierarchical structures, as proposed by several authors, truly exist within submarine fan deposits? And to do this, we'll be applying reduced complexity stratigraphic form model to analyze the deposition patterns in submarine fan deposits, and also to develop and utilize quantitative metrics to assess the presence of hierarchical structures. So this is how previous studies have viewed submarine fan deposits to look like, where we have bed or bed sets stacking together to form lobe elements, and lobe elements stacking together to form lobes, and those stacking together to form the complex. So we'll be using these 4 scenarios in our model. We have the flat seafloor where there is no noise. We have the smooth one with some level of noise, and we have the very smooth noise, and also we have random noise. And the quantitative metric we developed are twofold. The first one is the cluster stress index, which tells us whether hierarchy exists or not. Higher value indicates likelihood of hierarchy, lower values indicate non-likelihood of hierarchy. Then the second metric, which is the hierarchical step metric, tells us the number of steps we have. And so combining these two, we use that to form an hierarchy regime. And to ascertain that these metrics work well, we developed some synthetic farm model, making sure that we have a totally deterministic and hierarchical one, and we know the number of steps then, to a totally stochastic one, which with no hierarchy at all. So when we apply our metrics on this model and we get the desired results, it gives us the confidence that what we've developed has worked. And also we use all this to form the regime that tells us whether the regime of hierarchy and the regime of non-hierarchy. So the spectrum was created by calculating for the cluster stress index as well as the hierarchical metric, step metric. As expected, the totally deterministic and hierarchical fan model has the highest value, and the totally stochastic has the lowest value. And we also calculated that for our model results and placed them in this spectrum to know where they fall in. And we realized that they fall between 20% and 30% random elements, with the no noise having the highest value and the raw noise having the lowest value as expected. So for the hierarchical step metric, we can see that for the totally deterministic, it gives us exactly the number of steps we have in the structure, hierarchical structure. We also see that it also preserves that hierarchical structure when the random element is just about 10%. But as soon as we get to 20% down to 100%, we don't have any hierarchy anymore. So we combine these two to divide the whole spectrum into the hierarchy regime and the non-hierarchy regime, whereby from 0 to almost 20, about 18% random elements we have the hierarchy regime, and from 18% downwards we have the non-hierarchy regime. And we place the result of our model, we realize that it falls just almost after we have the highest point where we can say hierarchy exists, with the one with no noise falling close to that bar. Further away, the one with the raw noise is further away from this boundary. So in summary, we see that submarine fan strata are commonly described as having a nested hierarchical organization of elements, but the quantitative evidence that we just looked at now does not support this interpretation. And also, we've developed two metrics which are called hierarchical cluster stress index as well as the hierarchical step metric. This stress index gives us idea whether hierarchy exists or not, while the step metric tells us the number of steps we have. And we use these two metrics on 10 progressively more randomized realization in order for us to form an hierarchy regime. And when we combine these two metrics on and apply it on the 4 scenarios that we have in our model, because our model is something that is close to in nature, something that is in nature. So when we applied these two metrics on the results for all the 4 scenarios, we realize that they fall within the non-hierarchy regime. So it tells us 2 things. Either the model itself is missing some key elements that are responsible for producing hierarchy, or the interpretations of outcrops and subsurface data that we have today are more complicated and less realistic than what we think. So thank you for listening. See you guys in ISGC conference.
All right, thank you again for the presentation. Again, with the recorded presentations, please do send your questions in on the chat. We will get those to the presenters as well. Now we're going to move into the realm of channels with a couple of talks focused on seismic attributes. So Heather Bedle from University of Oklahoma is going to be presenting to us on the applications of seismic attributes for deepwater channels.
So what I'm going to do, so I'm Heather Bedle. I'm actually going to also present for Karelia LaMarca. She had to be in and out this afternoon, so we combined those last 2 talks into one talk, so it's a little bit more seamless. So I hope that's okay, and I'm still going to try to stick to like a 15-minute combined together. So everything that I show on these case studies and everything is up on my group website, which is the ASPE group. We focus a lot on geophysics, and so what I'm going to be talking about today is taking the scale up much bigger and talking about what we can see about deepwater channel architectures and systems using seismic attributes and machine learning. So I just want to get started with not assuming that folks are familiar with seismic attributes, and what they are pretty much just math. So seismic data is this beautiful wiggle and many wiggles over a 3-dimensional space. And what we can do with seismic attributes is we can analyze, instead of just the seismic signal itself, we can focus in on the frequency, the amplitude. We can compare one waveforms to its neighbors. All sorts of fun math can be done. And so there's more than like 50 attributes, probably closer to 100 now. And they can help us see geologic structures, image stratigraphic differences, and even help us see heterogeneities between the rocks or the pore fluid properties. And so oftentimes in seismic interpretation, multiple attributes are employed in one study. And so just kind of a classic example of showing one of these, on the left-hand side, I have a time slice, so you can imagine it as a map view at like 1.184 seconds through a seismic volume. And this is just looking at what we would normally see with the seismic amplitude. We see, some features, some gray blobs, some black sinuous features. But if we run a seismic attribute, which is one of my favorite, called coherence, which compares the waveform to the one next to it, we can suddenly see that this is really a mass of overlapping channels in the shallow Gulf of Mexico area. So that's just showing you how we can bring out those visualizations of seismic data. And so I'm going to be talking about 2 areas today. The first one I'm talking about is in the upper left-hand side. They're both in the Taranaki Basin. I'm going to talk about the White Star area first. This is the Romney area. And then I'm going to move down to another area, the pipeline data set, a little bit further south in the Taranaki Basin, and then also show some synthetic data. But to start off in the northern part of the Taranaki Basin, I'm showing on the bottom left-hand side this beautiful vertical section through the seismic. So you can almost think about it as an outcrop. And what we've got about halfway through there is this very lovely complex channel system. And then I'm trying to point to you with my mouse here. I'll make it a little bit brighter with my pointer. Boom. Okay, so it's beautiful complex channel system. And so one of the classic ways that we look at channels in deepwater seismic is with a method called spectral decomposition, and that's been around for decades now. It's where we take the seismic signal, we can break out particular frequency ranges, and then we can combine them back together with like an RG, red, green, blue plot overlay. And so this is an example of that seismic channel shown more in a map view, where we can see the different iterations of the channel, how it changes sinuosity through time. And so to focus on some more of the new things that we're doing with seismic data related to deep water deposits, here is one of the newer methods, came about maybe 6 years ago, where we took the principles of spectral decomposition and we started applying them not just to the seismic data itself and the amplitude data, but also to coherence, so this edge detecting capability attribute that we have. And so on the left-hand side, I'm trying to show a chair display. So we've got a vertical section in red and blue, so that outcrop kind of look, and then we have a map view in the grayscale. And what we're seeing there is we've highlighted certain frequencies that really accentuate the different iterations of the channel. And we could see in orange dotted lines, this is kind of much more sinuous, and then that's overprinting a yellow, much straighter version of the channel when it was younger. We can also use multispectral coherence in the same way that we use spectral decomposition, taking 3 different frequencies and overlaying them over each other. And so I'm showing that on the right-hand side here with that same channel. And what this allows us to see is the channel edges, and we can see the thicker channels are in the cyan color because that's with the lower frequency, and then the thinner aspects of the channel are in yellow. So we can start bringing out more of the geometry of these channels, even though they're nothing like what a lot of these photos have been showing today. Another fun seismic attribute we've been using is reflector convergence. And so this is able to give us a more detailed insights in the seismic data where we have levees or mounding within the channels. And so I've got a couple of images, kind of sketches on the left-hand side to the middle of different cases of geometries we might expect in deep water channels, from having overbank and levee deposits to kind of differential mounding in the center of the channel. And all of those can be shown in the reflection convergence. So reflection convergence is showing us where the reflectors, so if you think to seismic stratigraphy, where the reflectors are converging together or diverging. And so high convergence, these pink and red colors are showing us parts of the channels where we see that kind of pinching out and that convergence of the reflectors. So these are some case studies that Satinder Chopra and me and some other collaborators worked on a couple of years ago. And overall, there's a whole lot of different seismic attributes that we can use, from total energy to look at amplitudes, which may give us information about lithologies. Sweetness is another great one in clastic sediments. It's a combination of the amplitude and the frequency of the seismic data. We've got like the relative acoustic impedance, which we can get some lithological variations from, and then reflector convergence and spectral magnitude are other ones that that we use often. And so I mentioned earlier on that we have dozens of different attributes we can use. And so here's another case study where I'm going to show how we start combining these attributes with machine learning to improve our interpretations even more. And so this is one of Karelia's studies that she did a little bit further south in the Taranaki Basin as part of her master's work. So she originally started with Dr. Roger Slatt when she came to OU, and then with his passing, she came and worked with me, so we were able to combine all of her deep water channel knowledge with geophysics, which is more of my specialty. And so this is an image that she created for her master's work, just showing the different channel architectures we would expect in the deep water system. On the left-hand side, what we would expect them to look like with seismic, their internal shape, their external shapes. So doing some good classic seismic stratigraphy. And then we can look at what they would look like in vertical slice and time slice. And what I really want you to pay attention to is this image here on the right-hand side that I'm circling with my pointer. And so this is the amplitude data as it is, as we would get a volume delivered. And what I'm going to show you next is what that could look like with different seismic attributes and also machine learning processes applied to it. And so if we look at it, I mean, we know we're talking about channels, so you can probably guess that there are some deep water channel systems kind of hidden in there. And so the first thing we would do is we would think about, all right, which seismic attributes help us out and help us see more patterns in the seismic data that then we can relate to geologic analogs. And so what I'm showing here are 4 seismic attributes. We've got GLCM entropy in the upper left-hand side. This is what we call a texture attribute. So it compares the kind of like rubbing your thumb on your shirt or sweater. It compares the texture of one part of the map to the one next to it. It's used in image processing quite a bit. And so we could do the same thing with seismic data. We've got in B, the RMS amplitude, so root mean squared amplitude, and this is an amplitude attribute where we're highlighting changes in the amplitude, which can be related to velocity, density differences in the rocks. Down on the lower left-hand side, we have one of our edge detecting attributes. This one's the Sobel filter. It's a coherence or similarity style attribute. And so this one really highlights the edges of the channel and even some sediment waves that we're pointing out here with the blue arrow. And then we've got our spectral attributes, another category that can highlight the thickness differences in the system. And so taking all of those together, we can see that some of these attributes are working really well for imaging and bringing out the patterns of the channel complexes, other ones for the sediment waves, some splays and kind of fan-like architectures. But of course, what we want to know is, okay, well, if we have dozens of attributes, how can we look at them and kind of analyze them in our brains all at once? And the key to that is using machine learning. So machine learning lets us input, in this case, I'm showing 5 different inputs, but pretty much we think about the attributes as different dimensions of data. And so we can do this multi-dimensional analysis with clustering techniques. And so these are the results for that one system in the Taranaki Basin. We ran 3 different self-organizing maps, which is a clustering technique. So in each one of the SOMs, if the colors look similar, that means they are similar in all of the attributes. And so all of these have slightly different inputs that I'm showing up here on the upper right-hand side, but we can notice, in any one of these maps, we could pick out some of the channels in the area. We've got, let's see, some splay-like fans and kind of the dark purple. And luckily, Karelia, with her immense geologic knowledge, made some lovely cartoons to kind of help you see what we're able to see in the seismic data. And just to compare that to the original amplitude data, hopefully you can see the stark difference in what we're able to see in these systems when we take seismic attributes and machine learning. This is another case that I wanted to show from one of my master's students a few years ago. So Lara had looked at the Carnarvon Basin, Northwest Australia, doing a similar machine learning workflow with SOMs and some different attributes. Again, she could pick out different elements of the channel architecture, from the channel fill to mass transport deposits, kind of highlighted with the blue arrows, larger sheet sands pointed out by yellow. So I just wanted to show you all what can be done with seismic data. But this kind of led to the question, and this is what Karelia finished her PhD in last December. As we start to use machine learning more and more, my research group, and other people, we start to think about, okay, well, are we doing this right? There's a lot of machine learning methods, there's a lot of attributes out there. So some of the questions we've been asking ourselves the last couple of years is thinking more about, are we using the right attributes? Are we using the right parameters to really characterize the channel architectures? We don't want to overinterpret what we have in the seismic data. We also started to think about if we can assess the uncertainty in machine learning methods in terms of the uncertainty in our interpretations and also the uncertainty in what these methods are revealing. So those are some of the questions that we really wanted to focus in on, and these were the core of Karelia's PhD thesis, which is available up on our website for you to look through. So these are kind of like the 3 main chapters of research she did, and I think she's online at least until 3 to answer questions. So for this work, what we wanted to do was not take seismic data where we don't know the truth, but rather create a synthetic model based on realistic data where we could run the algorithms and then compare our answers to the true answer. So what we did is we teamed up with Lisa Streit, who gave us some data from the Chile slope systems where they had collected outcrop information in the Tres Passos formation down in Chile, and then created 3D models from the outcrops, which were then turned into synthetic seismic data. So now we have our seismic data, and we also have the true answer behind the seismic data. And so that allows us to test out our methods. Just to highlight a few things, I can't capture Karelia's work in 3 minutes, all the things she looked at, is here's a comparison. On the left-hand side, we have 30 hertz seismic data, which is more of the vintage seismic data, so maybe from the mid to early 90s. And then on the right-hand side, we have 60 hertz frequency data, so it's higher frequency. We can observe a little bit more. It's more modern, so more of what we're shooting actively, in the last decade or so. And so some of the things we really find is the extent of stratigraphic mixing, depending on what frequencies we have available between the different elements of this complex channel system. Other things we looked at with this synthetic data is comparing 2 different clustering methods. So this is unsupervised machine learning. We have the self-organizing maps, the SOM method, and then generative topographic maps, which is another similar method that allows a little bit more flexibility in fitting the data. And so just these 2 side-by-side comparisons, we can notice that GTM tends to have a more robust representation of the expected facies. So we're looking at a map view of these facies from that synthetic data set. And I just wanted to throw out that right now our research group, we've been testing out GTM over SOM, which was maybe more of the hot thing a few years ago. And we're finding that the GTM clustering method, unsupervised clustering method, is working really good for a whole bunch of different applications. Besides channels, it's working great for faulting, for fluid discrimination. So right now it's one of our faves. And then just to kind of highlight uncertainty. So I know a lot of folks, machine learning, it's like a black box. We want to understand what's going on there, like how close are we getting to the true answer? And so with this data set that Karelia had in synthetic seismic, we knew the different elements of the channel complex. We knew where the channel axes were, where the channel off-axis facies were, the mass transport deposits. And so she was able to run random forest training, so creating pseudo wells and telling the algorithm, okay, well, here we have a channel axis, here we have the MTDs. Can you detect what's going on in the rest of the seismic cube? And we found that, we found a lot of things, and the models are pretty good. And you can kind of see in this chart on the left-hand side, the true model versus the predicted model using random forest. In areas where we didn't train the data as well, there was quite a decrease in the accuracy. And so I just want to leave, I've got one more slide after this, but I kind of wanted to leave with the idea that so far, like my group, we focus on machine learning and seismic data. There is no one size fits all answer to getting geologic information out of the seismic data. But we feel like we're really starting to understand what works in different scenarios and what works in other scenarios. Some of the limitations of what we can geologically interpret in the seismic data with different methods. So from unsupervised methods to supervised to neural networks. And so the last thing that we've been working on, myself and my postdoc, is trying to start peering into these black boxes. So what I'm showing here is a method called SHAP. We have some code and we're working on some LIME investigations. So lots of acronyms in our realm of geophysics. But what this allows us to do is look at the model after it's been classified and then understand, okay, well, if this is salt, so that orange color is salt, what attributes are telling the algorithm that it's salt? Or if this is a mass transport deposit, which different attributes are telling it that's a mass transport deposit? And so that's kind of a quick overview of many of the things that we've been doing with seismic data for channels. And so I like to acknowledge my my students, Karelia, who's now at BP, same with Laura, my postdoc, David. You know, I've got a lot of student researchers doing a huge variety of projects, and then our sponsors who help fund the students.
Excellent. Thank you so much, Heather. That was a great talk.
No problem.
And good job taking 2 talks and getting it, tightening up the timeline. Great job.
My pleasure. And Crowley, I think is still around, so.
Okay, perfect. Well, because we were able to capture some time back, I wanted to kind of open it up for some questions. If there, you know, I don't know if I can't see the questions on my end right here, but if there's some key questions, please do add them. Stan, if you've seen any questions pop up, feel free to read those out. But it looks like there's nothing right now. But what I would do is encourage anybody to add questions. Again, you know, while I'm talking here and we finish up the rest of the afternoon, we will get all those questions out to everyone. So I think, you know, while people had questions, one of the things that was interesting, if you just look at the full range of talks that we had, is the breadth of approaches and questions people are asking on deep water, right? Deep water is a huge range of processes, huge range of architectures, huge range of implications on the oil and gas industry, understanding climate, understanding carbon cycles, understanding carbon storage. So approaching, you know, this problem is not just an industry problem or specifically a hydrocarbon industry problem. It's a series of scientific questions that we have from a multitude of perspectives. And we need to address those from a multitude of perspectives as well. And I was just, you know, kind of going through all the talks again, kind of just like listening to everyone. And I thought it was it was really exciting me to see where we're going in deep water, right? It's not everybody asking the same question or everybody focused on the same type of feature or the same basin. But if you look at the talks that we had Kevin and Nora and Jengang talking about 3 very different types, or Jorge as well, talking about 3 very different types of outcrop systems, right? We're using these outcrops as major data points to generate and develop models. And then we have Jaco, Anne, and Zane that are kind of testing our concepts, you know, asking questions. Is there a similarity between carbonate systems and clastic systems? What are the controls on deep water depositional systems, and how does our understanding of those controls actually change with time when we have higher versus lower resolution data? And then you have Ibrahim that was asking, you know, we talk about deep water lobes or deep water fans as being hierarchical. Well, let's actually test that model. Let's test that hypothesis there. And Anne was taking a nice example of looking at, you know, maybe a model that had been put together in terms of how deep water canyons form, how deep water canyons look, and actually, again, testing the range of uncertainty on how those may look in the formative processes for those. And then I thought it was really nice with Heather and Karelia ending with, again, actually looking at seismic, looking at different approaches to evaluating that seismic, and then having to pull some work from outcrops in Chile to try and, again, interpret what we're seeing and leverage these tools to actually address that. So very exciting to see that our deep water community is approaching multiple questions from multiple perspectives, from outcrop to seismic to models, whether those are numerical or conceptual or flume examples, with Zane's adding that nice kind of flume video in there. I do see that we had some hands being raised for a question. I cannot see that, so if any of the organizers can read that.
I think apparently they had left now. The person
Oh, maybe it was a wave then.
Yeah.
Yeah. Excellent. Well, Stan, I didn't know if you had any more points that you would wanted to add to this. We will be sending out the recordings, as well as the poll answers, the polls and the questions that we gather from here. But again, very much, we very much appreciate everybody attending and taking the time out of their day to listen to these excellent presentations, and very much thank you to all the presenters for the research that you're doing and your willingness to present it here. Very much thank you on behalf of Lillian, Emma, Stan, and myself, and the SEPM Deepwater Group, and Cassie, thank you for controlling everything in the background for us, because left to our own devices, it wouldn't have gone well.
Yeah,
Okay.
that's a great synopsis. Thank you very much, everyone. There's a suggestion here that we get all the speakers on the screen to take a screenshot before everyone departs. So if you're a speaker, turn your video on if you're able. Notes of support and thanks coming in here. That's appreciated.
All right, I will volunteer to take a screenshot. All right, excellent. Oh, it froze. Let me do it one more time. All right, here we go. 1, 2, and 3. Excellent.
Okay.
All right, well, again, very much thank you to everyone for your time, and hope everyone is leaving this excited about new outcrops that they haven't seen yet, and ones that we will all get to see at some point. New techniques, new learnings, new models to test, and some French lessons from Zane.
Very good. Okay.
Yeah,
Thank
next meeting in the field, eh?
Yeah, that's the goal.
I hope so. That'd be nice.